My name is Emily Trezza, and today I'll be discussing the orbital dynamics of asteroids and Saturn's gravitational influence. This presentation highlights my research on how Saturn's weaker gravitational effects compare to Jupiter's well-documented impact on the asteroid belt. So, some background. The asteroid belt lies between Mars and Jupiter and contains millions of rocky objects. These objects are influenced by the gravity of nearby planets, particularly Jupiter. Now, an important concept of this presentation is orbital resonances. Orbital resonance occurs when two objects in space, like planets or asteroids, have orbits connected by a simple ratio such as 2 to 1. This creates a repeating gravitational pull that disrupts stable orbits over time. This disruption results in fewer regions of the asteroids known as Kirkwood gaps. So, in this image, it basically describes what Kirkwood gaps are. So, the distribution of objects in the main asteroid belt is not uniform. Regions known as Kirkwood gaps contain very few asteroids, and major gaps occur at locations of orbital resonance with Jupiter, and in the image you can see the visible gaps that there are due to Jupiter. So, research indicates that Jupiter's strong gravitational pull creates pronounced Kirkwood gaps. This is proven. In contrast, Saturn's gravity is weaker, making its influence more subtle and harder to detect. Previous studies suggest that Saturn's orbital resonance might play a role in asteroid orbits, but this remains largely unexplored. The goal of my research is to identify whether Saturn's gravitational effects can produce detectable patterns in the asteroid belt. So my hypothesis for this project is, if Saturn's gravity significantly influences asteroid distribution, detectable patterns aligning with Saturn's resonances will emerge in the asteroid belt. These patterns will be weaker than those caused by Jupiter, but should still stand out when compared to randomized models. On to my procedures. So first I needed data to work with. I collected data on 100,000 asteroids from the International Astronomical Union's Minor Planet Center, a public database for asteroid information. From there, I found each asteroid's eccentricity and semi-major axis data. For context, eccentricity is how stretched or oval-shaped an orbit is. So a perfect circle has an eccentricity of 0, while a more elongated orbit has a higher value closer to 1. A semi-major axis is half the longest distance across the orbit. It's like the radius of the orbit's widest part and helps measure the orbit's size. So Kepler's third law was verified. It applied to estimate orbital periods for the asteroids. For reference, an orbital period is the time it takes an object to complete one full orbit around the sun. Then I plotted my asteroid data into a histogram, and finally marking the resonances corresponding to the Saturn and Jupiter to identify the patterns. Here's a photo of the final graph made by me using the programming language Python. Most of this project was done through Python, such as the calculations, graphing, carrying out some of the simulations I would use later in the experiment. And I would put in my commands and the output would be different histograms. Here's the first one. As you can see here, Jupiter's resonances fall between those huge gaps in the histogram, which are the Kirkwood gaps. We also have Saturn's resonances in red lines, which also falls in some of the dips in the asteroid distribution. Here we're testing to see if that's a coincidence or if it has meaning in that Saturn's gravity did that. Then I had to calculate gap percentage of the asteroids in the histogram. Now, gap percentage is the measure of how much an observed gap in the asteroid distribution stands out compared to what we'd expect if the asteroids were evenly or randomly distributed. Essentially, it quantifies the gap depth or significance of these gaps. A high gap percentage means a prominent gap depth, while a low gap percentage indicates no or little or no detectable gap. So first, I commanded Python to average asteroid densities in each bins adjacent to Saturn's resonances. Then I compared that central bin corresponding to whatever resonance density to the adjacent bins using the formula. Gap depth percentage equals average bins minus central bins divided by average bins times 100. Next, I generated 10,000 randomized asteroid distributions in Python to simulate random gaps. I compared these simulated gaps to the actual gaps, the parts of the histogram where Saturn's resonances lay, using statistical analysis, specifically p-values. A p-value is a number used in statistics to measure how likely it is that the result of an analysis happened by chance. It helps determine whether the observed effect, like a gap in asteroid distributions, is significantly significant. A low p-value, less than 0.05 or 0.08, means that observed results are unlikely to be due by random chance and are statistically significant. A high p-value, on the other hand, greater than 0.05, means that the results could easily have happened by chance, suggesting no significant effect. Essentially, it helps us determine whether those patterns we observe are meaningful or just randomized. So to visualize this data, I created histograms representing asteroid distributions and resonances. I then used these histograms to compare and randomize gap depths. Jupiter's resonances were used as a control to validate my methods, as well as its significant influence on the asteroid belt is well established. So on to my data and my results. This table summarizes the key results of my analysis, comparing the gap percentages and p-values for Saturn and Jupiter's resonances. Let me walk you through what this table represents and what it tells us. The first two columns show the resonance and ratio of Saturn's resonances used. Next, the p-value column helps us evaluate whether these gaps were statistically significant. For Saturn, the p-values were quite high, such as 0.6092 and around that. So, after the whole procedure was done in Python, my output was a series of graphs that shows the p-values of each Saturn resonances, one resonance per graph, and Jupiter's resonance as a control, which was always at the 3 to 5 resonance. Here we see Saturn's most significant p-value, or when Saturn had the smallest p-value, signifying that it could be significant. However, compared to Jupiter, it's not very significant at all. In this graph, we see Saturn's p-value with the highest, that has the highest, and this therefore is the least significant with a p-value of 0.620, which is very high. So my key observations are as follows. Saturn's values are very similar to the random values found in Python. High p-values like 0.6 for Saturn's resonances indicate no statistically significant gaps compared to Jupiter and the random gaps. Jupiter's p-values being less than 0.08 prove that they are statistically significant, proving the validity of these methods. Saturn's gap resemble random variations, which means that there was weak gravitational effects detected. So, in conclusion, Saturn's resonances are statistically insignificant compared to Jupiter's. This supports the hypothesis that Jupiter's gravitational pull is far more influential. So, for future improvements, I propose, first, including more asteroids from the AIU Minor Planet Center to increase the resolution. Second, we could analyze a broader range of resonance points for Saturn, giving us more results that we may have not found by just using 8. Third, I could use adaptive binning to enhance sensitivity near resonance regions. And fourth, investigating overlapping influence of Saturn, Jupiter, and other planets to refine the understanding of their combined effect. So for the next steps in research, first, this could explore how Jupiter and Saturn together influence asteroid distribution. So you could adapt this methodology to include this as a factor. Then you could apply methodology to the Kuiper Belt objects and examine outer planet resonances in the solar system. And for long-term applications, you can enhance models of our planetary system formation and evolution. This can help understand where we live and where we are. And it could also assist with exploration and understanding of other star systems with asteroid belts or exoplanets. So thank you for taking the time to explore this journey through orbital dynamics with me, and I appreciate your attention. Thank you.